Hi students, in the last session we had learnt how to specify a point on a ray, that is designation of a ray vector. It is given in terms of two coordinates. One is x, which is the distance of the ray at that point from the axis of symmetry, and the second coordinate is lambda, which is the optical direction cosine. And optical direction cosine lambda is equal to mu sine alpha, where mu is the refractive index of the medium through which the ray passes, and alpha is the angle that it makes with the axis of symmetry. So any ray vector is specified by the two coordinates x and lambda, and it can be represented by a column matrix x lambda. Okay, it is a 2 by 1 column matrix. Then we uh, studied that any ray, when it comes in an optical system or when it falls on an optical system, say like a lens, it can undergo two operations. One is either height of the ray will change, that is either the ray can undergo translation or the ray will change its direction and because it is undergoing refraction. So it can undergo two operations which are translation and refraction. Now, how do we represent the result of a translation operation and the result of a refraction operation? Here, the translation operation is represented by a translation matrix and the refraction operation is represented by a refraction matrix. So, in matrix method, how do you represent a refracted ray or a translated ray? There is an incident ray represented by the coordinates or the column matrix x1 lambda 1, and if that ray is undergoing refraction, x1 lambda 1 എന്ന കോളം മെട്രിക്സിനാൽ റെപ്രസെന്റ് ചെയ്യപ്പെട്ട ഒരു ഇൻസിഡന്റ് റേ റിഫ്രാക്ഷൻ സംഭവിക്കുകയാണെങ്കിൽ മെട്രിക്സ് മെത്തേഡിൽ നമ്മൾ ഇതിനെ മാത്തമെറ്റിക്കലി എങ്ങനെ റെപ്രസെന്റ് ചെയ്യും? അപ്പോൾ നമ്മുടെ റിഫ്രാക്റ്റഡ് റേയുടെ ഫൈനൽ ആയി കിട്ടുന്ന റിഫ്രാക്ഷൻ സംഭവിച്ചതിന് ശേഷം കിട്ടുന്ന റിഫ്രാക്റ്റഡ് റേയെ റെപ്രസെന്റ് ചെയ്യുന്ന കോളം മെട്രിക്സ് x2 lambda 2 ആണെങ്കിൽ x2 lambda 2 is obtained when the refraction matrix operates on your incident ray. That is the column matrix x1 lambda 1. If matrix A, small b, small c, small d represents your refraction matrix, then how do you get your final refracted ray represented by x2 lambda 2? The refraction matrix, which is an operator, must act on your incident ray, which is represented by the column matrix x1 lambda 1. Similarly, if the incident ray represented by x1 lambda 1, column matrix x1 lambda 1 is undergoing a translation, means this same column matrix must be acted upon by a translation matrix so that you get the final position of the translated ray given by x2 lambda 2. So I hope it is clear. So just by doing the mathematics, you get the designation of the final ray. That is, when you get x2 and lambda 2, you get the position of your ray, and from that means by knowing the column matrix x2 lambda 2 from the axis of symmetry, how far is your final ray, or where do you get the final image? Then what is the angle that the final refracted ray makes with the axis of symmetry? All these information can be obtained without tracing the ray diagram. So that is the advantage of this method. Okay. So what you have to do now is, if you are given the designation or the coordinates of the incident ray, then you must have the refraction matrix with you to find out the designation of the final ray vector. Similarly, if you are given the position of the initial point or some point on your incident ray, then how will you get the final position after translation? How will you get x2 lambda 2? For that, you must know the translation matrix which must act on x1 lambda 1. So, our function or what we have to do next is find out how should be your translate. This is a very general form that we have given here, a b c d. The components in the matrix or the elements in the matrix have not been specified, so you have to find out what will these a b c d be for a translation matrix, what will a b c d be for a refraction matrix. That is what you are going to do next. That is, we are going to find out the exact shape or form of your translation matrix. For that, we are going to consider this figure. So this is my ray PQ. So it began at P, that is the initial point, and it is going to the point Q. That means in going from P to Q, the ray is undergoing a change of height. There is no change in the direction, it is simply undergoing a change of height, which means the ray is undergoing translation. Now, what is the specifications here? That is, the ray is traveling in a homogeneous medium. There is no change in the refractive index of the medium. It is going through the same medium, having a refractive index mu. Then let x1 alpha 1 be the coordinates of the ray at the point P. At the point P, its coordinates are its height from the z-axis is x1 and the angle that it makes with the z-axis, that's the axis of symmetry, is alpha 1. So its coordinates there are x1 alpha 1, and at the point Q, let its coordinates be x2, the total distance from the z-axis, and the angle that it makes, that is alpha 2. Okay, so since the medium is isotropic, I told you the ray is passing through a homogeneous medium having constant refractive index, so there will be no change in direction, or alpha 1 will be equal to alpha 2. So we have all these information with us. Now, we have to find out A, B, C, D, the values of the elements A, B, C, D in the translation matrix. For that, what we do is drop the perpendicular PP dash from P to the Z axis, that is PP dash, and I drop another perpendicular from Q to the Z axis, that is QQ dash. Let P dash Q dash, this distance here be, that is a separation between P and Q, be capital D. Now, consider the triangle PQR, this one, the right triangle PQR. Then what is tan alpha 1? Tan alpha 1 is equal to opposite side by adjacent side. Opposite side is QR by PR. What is QR? QR is equal to this total height minus this height Q1R. So total height is x2 and the height Q1R is equal to x1, this height. So QR is equal to x2 minus x1 divided by PR. PR is equal to the same distance, P dash Q dash. So that is capital D. So I get QQ dash minus QR dash, that is x2 minus x1 by capital D, is equal to tan alpha 1. So that x2 minus x1 by D is equal to tan alpha 1, or x2 is equal to x1 plus D tan alpha 1. For very small angles, tan alpha 1 is equal to alpha 1, nearly equal to alpha 1. So I get my first equation, x2 is equal to x1 plus d alpha 1. Next, we write down the optical direction cosines for the points P and Q. At P, the direction cosine is lambda 1, optical direction cosine, that is mu 1 sine alpha 1. For small angle, I can write sine alpha 1 as simply alpha 1, so it is mu 1 alpha 1, and lambda 2 is equal to, it is mu 2 alpha 2. But since both are both the points are lying the same medium, I write it as mu 1 alpha 1 and mu 1 alpha 2. But we know that since the medium is homogeneous and isotropic, alpha 1 equal to alpha 2. So lambda 1, lambda 2 is equal to, both are equal, that is lambda 1 is equal to, lambda 2 is equal to mu 1 alpha 1. Okay, so what I do is lambda 1 is equal to lambda 2, and from this equation I get alpha 1 is equal to lambda 1 divided by mu 1. Alpha 1 is equal to lambda 1 divided by mu 1. In the first equation that we wrote down in terms of x2 equal to x1 plus d into alpha 1. This alpha 1 I replace it with this value, that is alpha 1 I replace it with lambda 1 by mu 1. So that my equation 1 becomes x2 is equal to x1 plus capital D lambda 1 by mu 1. Now I have got two equations, equation 2 and equation 3, that is x2 is equal to x1 plus d lambda 1 by mu 1 and lambda 1 equal to lambda 2. Now why did I do all this? What we have to find out is this matrix A, B, C, D. I should get the specific elements A, B, C, D for a translation matrix. We know that the general matrix equation followed here, whether it is translation or refraction, whatever is taking place, the general mathematical equation that you can write is the final ray column matrix x2 lambda 2 is equal to, here it is undergoing translation, so the translation vector will act on the incident ray vector, which is represented by the column matrix x1 lambda 1. Now you simply, this equation I'm going to simplify it. So what will I get? I just do the matrix multiplication. So you get x2 is equal to a into x1 plus b into lambda 1 is equal to x2. What is lambda 2 equal to c into x1 plus d into lambda 1. So these are my equations 4 and 5. Now what I'm going to do is, these two are general equations. Okay, general matrix equation, if any operator A, B, C, D will act on x1 and lambda 1. If any matrix operator A, B, C, D will act on x1 and lambda 1, you get two equations like this. But we know that for translation, when the ray undergoes translation, x2 should take this value and lambda 2 should take this value. So what I am going to do is I am going to compare equations 4 and 5 with 3 and 2. Comparing equation 4 and 3. What do I get? You compare equation 4, this 4 for x2 and this x2. Why? Because this is the specific case for translation and this is the general equation. So x2 on both LHS, both sides you have x2. On RHS, you have, here you have ax1, here you have the coefficient of x1 as 1. And here you have the second term b lambda 1 and here you have the coefficient of lambda 1 as capital D by mu 1. I think you understood now why we replaced this d alpha 1 by lambda 1 by mu 1, because this is for comparing with the general equation. Otherwise, you won't have a lambda 1 term here. That is why we replaced alpha 1 with lambda 1 by mu 1, so that you can compare it with this equation 4. Otherwise, if you write here alpha 1, you have nothing to compare in the second term. So you get d is equal to d by capital D by mu 1. And what is lambda 2? Lambda 2 is equal to lambda 1 in the case of a translation operation. And in the general equation, you have lambda 2 is equal to cx1 plus d lambda 1. When you compare 4 and 2, you get c is equal to 0 because there is no x1 term here, and d is equal to 1. So that I get my A, B, C, D as A, small a is equal to 1, small b is equal to d by mu 1, c equal to 0 and small d equal to 1. So the translation matrix can be specifically written as t is equal to 1, d by mu 1, 0 and 1. So this is the translation matrix which must act on any incident ray column matrix, so that you get the final column matrix of the final ray after translation. So for finding out the final position or the final ray vector after translation, you have to make this translation operator act on your incident ray vector x1 lambda 1. Okay, so this is the exact representation of the translation vector. Then determinant of t. We are simply finding out the determinant of t, that is 1 d by mu 1 0 1 is equal to 1. Okay, so the determinant of my translation vector is t. So when a ray moves between two optical systems through a distance d in air, if the medium through which the ray moves is air, then my translation matrix reduces to t is equal to 1, then d, because mu1 is equal to 1 for air, and 0 and 1. It reduces to this form. Okay, so I hope translation matrix is clear to all of you. Please go through the notes and contact me if you have any doubts. Thank you.